Hello, my dear little bugs. Welcome back to my channel yet again. So, today we'll be speaking about the topic that is determination of alkalinity of the water. So, in this particular video, we will be discussing what is alkalinity, along with that, how to perform this particular experiment, and what are the applications, why we are actually performing or conducting this experiment in the laboratory. Okay, so when we speak about alkalinity of water, okay, alkalinity is nothing but the ability of the water that is to neutralize the acid content present in the water. Okay, so when we speak about neutralizing the acid content or the acidity in the water, tells or it means that the water is now basic. Okay, so it acts as a buffer, okay, that is going to resist the change in the pH of the water. That's the basic thing what you mean by alkalinity of the water. Okay, so generally when we speak about water, pH is actually remains neutral, okay, but the alkalinity of the water is generally impaired by different sets or different kinds of salts, okay. Okay, so you will be having hydroxide ions, carbonates ions, bicarbonates ions. These are kind of like these are in the huger amount and they majorly or generally causes alkalinity in the water. Okay, but even along with these carbonates, bicarbonates, as well as hydroxides, we have silicates, we have phosphates, we have borates, okay, and many other ions. Even they also lead to the alkalinity of the water, but they are present in a lesser or the smaller quantities compared to your hydroxide carbonates as well as bicarbonates. That's why we are not considering silicates, phosphate, borates, and other ions. Okay. Now, when we speak about base, okay, when we speak about the base, we all know that it's actually going to neutralize the water, but the base is not going to dissolve in the water. Okay, that's a concept. Okay, base is going to neutralize the water, but it is not going to dissolve in the water. But there are certain types of base called as alkali. Okay, so alkali is also going to kind of like a neutralize the water, but it's going to dissolve in water. That's make a basic difference between what are alkali and what are bases. Okay, now alkali is a type of base, but it's going to dissolve in water. So all alkalis are bases. Not all the bases are actually alkali. Okay. Now, to check the alkalinity of the water sample, we will be using acid-base titration. Okay. Basically, for performing the acid-base titration concepts and all, we'll be using two indicators: phenolphthalein indicator as well as the methyl orange indicator. Okay, so alkalinity is expressed as a total alkalinity as well as phenolphthalein alkalinity. We'll be discussing in the further slides. Okay, and the results, okay, it's actually measured as mg per liter of calcium carbonate. Okay, it's actually going to tell the operators or any kind of like chemist how much acid, okay, the water can absorb before the pH starts to drop. For that, we'll be actually measuring it in mg per liter as calcium carbonate. So now I have just made a table over here. Okay, so this table indicates, okay, a phenolphthalein as well as methyl orange indicator. When we speak about phenolphthalein indicator, methyl orange indicator, and all, now phenolphthalein is a kind of like a weak acid. Okay, now this is a very much kind of like a weak acid indicator, and methyl orange is a strong acid indicator. And the pH range of this phenolphthalein is ranging from 8.2 to 10. Okay, and methyl orange is 3.1 to 4.4. Okay, now usually phenolphthalein indicator is colorless. Okay, so the phenolphthalein indicator is colorless, but in the basic condition, okay, but in the basic condition that is from 8.2 to 10, okay, so this phenolphthalein indicator turns into pink color. Okay, so usually in the acidic condition the phenolphthalein solution is colorless, but in the basic condition or in the basic solutions, okay, it turns into pink. Okay, the vice versa will be your methyl orange. Okay, methyl orange is somewhat like in the acidic condition, it will be somewhat like reddish orange or red. Beyond 4.4, it turns into pink. Okay, after if you just consider acidic in the basic condition, it will be somewhat yellow in color. So if your water sample is somewhat basic, when you add methyl orange indicator, it will be somewhat yellow in color. Okay, but if your water sample is not basic, at that time it will be somewhat orangish in color. Okay, fine. Now, why we are actually conducting this experiment, or what is the use, or what is the application of doing this experiment? Okay, the first thing you should understand that now alkalinity is actually going to play a key role in water as well as the kind of like a waste management treatment and all, because it's going to regulate the pH. Okay, and determines how the chemical is going to react in a kind of like a treatment process. Okay, so the first thing or first foremost application I would say is a coagulation. Okay, so when we speak about the coagulation, what is coagulation? Okay, coagulation is the process that is of removing the suspended solid matter or an organic matter or any kind of like a turbidity from the water. Okay, by adding certain coagulants. So you're removing all the suspended solid particles or organic particles or turbidity stuffs from the water by adding certain coagulants. Maybe the coagulants like commonly used coagulant is alum. Okay, you'll be adding ferric chloride, you'll be adding ferric sulfate. So these are the coagulants. So when you add the coagulants to the water which contains these suspended solids or whatsoever, so they cause, now when you add this coagulant, they will cause a clumping. Okay, so when they clump together, now we will be calling it as flocks. It will be easy for us to remove these particular flocks. So for coagulation, okay, we will be requiring alkalinity. It is going to happen only in the basic condition. If the water is basic, okay, when you add the coagulants like alum, okay, they help in formation of the flock. So for that reason, alkalinity test is very much needed. Okay, so that is one of the main thing. If alkalinity is too low, okay, when the water has a kind of like a very low alkalinity, so when you add coagulants to that, okay, so the lower in the pH drastically, okay, so at that time, okay, your coagulation process is ineffective, okay, okay, and what is going to happen? This cause acidic water which corrodes your pipe, okay, or your infrastructures or whatsoever. So for that reason, okay, if you are actually having kind of like a acidic water, if you add an alum, you are not having that flock. Okay, so if you want to have that flock, you require the basic water. Check that you will be doing acid-base titration. Next one is softening. Okay, so purpose. What is the purpose of this particular? What is softening and all those things? So if you want to remove the hardness, okay, hardness causing ions, hardness of water. There is a different experiment. Okay, to check the hardness of water and all. Okay, so to remove the hardness causing ions, like you have calcium ions, you have magnesium ions. Okay, so using certain kind of like what you can say lime or soda ash, if you're using it, okay, that leads to softening of the water sample. The role of alkalinity now. Okay, so lime is going to react with the bicarbonate. Okay, we have already discussed bicarbonate, carbonate, as well as hydroxide leads to alkalinity. Okay, so when you add lime to the water sample, okay, so it reacts with the bicarbonate or it reacts with the carbonate alkalinity, that is to form the precipitate. Okay, the amount of alkalinity is going to determine how much lime or how much soda ash is actually needed for softening the water, okay, or the water sample, okay. The alkalinity is too low, okay. So if the alkalinity is very much low, more chemicals is actually needed, or the process may actually fail in the end, okay. So if the alkalinity is low, more chemicals is needed. Vice versa, if the alkalinity is very high, less chemicals will be required, okay. The third one is anaerobic digestion. Okay, so when we speak about anaerobic digestion, okay, so it's a kind of like why we'll be requiring it. Okay, so what is anaerobic digestion? You're breaking down the organic matter, okay, in the wastewater, kind of like wastewater sludge, okay, without oxygen, okay, and you're producing the methane in the end. Okay, so why we are doing alkalinity test for anaerobic digestion process or whatsoever. Okay, so anaerobic digestion process again, so you will be requiring alkalinity test. Okay, so alkalinity buffers the system against the acid buildup from the volatile fatty acids and all. Okay, so it's going to maintain overall the stable pH like 6.8 to 7.2 kind of like pH it's going to maintain, which is very much crucial. Okay, that is for kind of like a microbial activities or whatsoever. So lower alkalinity leads to acidification and the process will be actually failed in the end. Okay. So what the operators are going to do? Okay. Okay. So what they'll be doing? They'll be using alkalinity curve value to adjust the dosing of the alkaline substance. Alkaline substance on the head, you will be having sodium bicarbonate, other things. Okay, so to check how much grams or how much mg or liter of sodium carbonate has to be added so that they can maintain the entire unit. Okay, so for that they'll be checking the alkalinity. They'll be determining the alkalinity of the water sample, or it will be the wastewater sludge. Okay. So, overall, if I want to say, alkalinity is very crucial. That is to control the kind of like a parameters in the kind of like various different treatment processes. Okay, it mainly aids in the operators, mainly determine the correct chemical dosages. Okay, not dosage, sorry, doses of the calcium carbonates or whatsoever, and prevent pH imbalances. Okay, in the water. Okay, and to ensure the stable as well as the efficient operation, you will get the proper results. Okay. So we'll start with, I have already spoken about hydroxide alkalinity, carbonate alkalinity. Okay. We'll be discussing about hydroxide as well as carbonate as well as bicarbonate alkalinity. Till now, we will be discussing about these a lot. So what are they? What are their role or what is their importance? Okay. So we'll start with the hydroxide alkalinity. So when we speak about this hydroxide alkalinity, OH minus. Okay. So as you all know, OH minus or hydroxide is a kind of like a strongest base out of all the three. Hydroxide along with that bicarbonate and carbonate, out of all these three, hydroxide is somewhat like a strongest base. Okay. And usually when we in the laboratory, if you're preparing the sample, okay, for alkalinity, just to get this hydroxide alkalinity, we'll be using NaOH, that is sodium hydroxide. Okay. Mainly it comes from these strong bases. If the water contains kind of like sodium hydroxide or lime, okay, so at that time you will be having the results for this particular hydroxide alkalinity. So usually there will be kind of like significant rise in the pH. Usually it is more than 10, like 12 or whatsoever. Okay, and it's not usually or commonly found in your natural water unless if you add the chemicals like NaOH or lime. You won't add NaOH. If you add lime to the water and all, at that time you will be having this hydroxide alkalinity. So most commonly in the natural water body, you won't be having this hydroxide alkalinity. Okay, so present, okay, when we do the titration, okay, so only when the pH is kind of like very high, okay, maybe 10 or 12, okay, the phenolphthalein is going to kind of like when you add, just imagine you are taking a water sample, okay, and you have added NaOH or you have added lime. Okay, so it will be when you add it, and when you add but 1 or 2 drops, 1 drop is more than sufficient if it is actually having sodium hydroxide in it. Okay, so when you add a drop of phenolphthalein, it turns into like a strong or dark pink in color. Okay, so it shows that there is a phenolphthalein alkalinity. It indicates that there is a, we can calculate for the phenolphthalein alkalinity. Okay, so it's very much kind of like when we speak, I've already told you, in a natural water body or in the drinking water, we don't have hydroxide and alkalinity unless and until we're going to add lime. Most of the time in the natural water body or whatsoever, for treatment purpose and all, we'll be adding lime. So at that time only we'll be having the hydroxide alkalinity. Okay. The next one is carbonate alkalinity, CO2 minus. Carbonate alkalinity. So it's a kind of like a moderate base. It's not a strong base, it's a moderate base, but it is stronger compared to your bicarbonate. Okay. So it's typically kind of like found in the water which has a pH range between 8.3 to 10. Okay. So if it is more than 10, it's hydroxide. If it is 8.3 to 10, you will be having carbonate. Okay. So it's actually formed by the dissolved carbon dioxide and chemical reactions like lime treatment and all if you're doing. So at that time you will be having the carbonate alkalinity. So we'll be doing another experiment showing how to calculate dissolved carbon dioxide. At that time I'll be speaking about this dissolved carbon dioxide entire scenario. Okay. So mainly if you are actually having dissolved carbon dioxide and if you're treating water with a lime, at that time you'll be having the carbonate alkalinity. Again, if you're taking a water sample and if you're adding a phenolphthalein indicator to it, turns into pink color. Okay, so that's a thing you should know that. Okay, so your phenolphthalein indicator, when you add it for the water sample, which ranges from 8.3 to 10 or 12, turns into pink in color. Okay, as we have already discussed, what is phenolphthalein indicator? In the basic medium, it turns pink. In acidic medium, it turns into colorless. If it is less than 8.3, it is not acidic if it is less than 8.3. But still, if it is less than 8.3, the pH, okay, if it is less than 8.3, your phenolphthalein indicator turns from pink to colorless. Okay. Now, the last one is bicarbonate alkalinity. So when we speak about bicarbonate alkalinity, it had CO3 minus. Okay, so it's a kind of like a most common form of alkalinity found in all kind of like normal waters. Okay, if you're considering normal waters, most probably you will be having the bicarbonate alkalinity. Okay, so pH range is somewhat like 4.5 to 8.3. So if the pH range is like that, you will be having the bicarbonate alkalinity. So mainly again dissolved carbon dioxide. Okay, so because of that, we'll be having the bicarbonate alkalinity. So here you should remember that phenolphthalein indicator is only going to give you the result that is pink color if it is ranging from the pH is ranging from 8.3 and above. Okay, like 10 or 12, we will be having pink in color. So phenolphthalein indicator for this particular water sample, if it is only containing bicarbonate, at that time you won't have pink color. Okay, the water sample, when you add phenolphthalein indicator, it doesn't turn into pink in color. So it indicates that your carbonate as well as your hydroxide ion is absent. What is present? Only bicarbonate is present. Okay, so for that, the remaining option is after phenolphthalein test, we'll be doing the methyl orange one. That is for testing total alkalinity. We'll be discussing that. Okay, so we'll be adding the methyl orange indicator. So will turn into somewhat yellow in color, and you will be actually titrating it with the acid that is maybe your zero point 0.1 normal HCl or sulfuric acid, and you will be getting the results in the end. Okay, so we'll be discussing that in the principal part. So I hope these three ions concept is clear, three alkalinity concept, that is bicarbonate, carbonate, as well as the hydroxide alkalinity. So we'll discuss about this again. Now this is there are different types of alkalinity: hydroxide OH minus, carbonate CO3 2 minus, bicarbonate HCO3 minus. Okay. So hydroxide obviously pH range should be more than 10, carbonate 8.3 to 10, bicarbonate 4.5 to 8.3. Okay. Strength, hydroxide is very strong, it's moderate and it's weak. Okay. So here you should remember that strong bases will lead to this hydroxide alkalinity. Natural or added alkalinity like limestone treatment and all, carbonate alkalinity. And if you have the carbon dioxide dissolved, okay, dissolved carbon dioxide in the natural water, then most of the time you will be having the bicarbonate alkalinity. Okay, so in the water treatment, okay, labs or in the laboratory to perform this experiment, we actually do a titration using two indicators, that is phenolphthalein indicator, either you can say P or you can say it as PO. You can either say it as P or we can say it as activation as PA. Okay, phenolphthalein alkalinity. Indicator is phenolphthalein. Okay, alkalinity test, whatever we are doing, that is phenolphthalein alkalinity. Methyl orange, I'll be using T. Okay, why T? Because if you are using methyl orange, we will be measuring the total alkalinity, that is T. Okay, so PA is phenolphthalein alkalinity. PA is total alkalinity. To check the phenolphthalein alkalinity, we'll be using an indicator that is phenolphthalein, abbreviated as P. To check the total alkalinity, we'll be using methyl orange, abbreviation. I'll be using it as TAT. Okay, so we'll be using methyl orange. Some people use M also as the abbreviation, just to tell that M means methyl orange. Okay, so I'm using abbreviation that is for total alkalinity, which is methyl orange over here. Okay, so when we speak about this phenolphthalein, okay, indicator, so it detects, okay, now phenolphthalein indicator, when we are speaking, it ranges, the pH is actually ranging from 8.3 to 10 or 12. Okay, so pH range will be that. At those pH range only, it will give you pink in color. Okay, so detects your hydroxide and half carbonate. We'll be discussing about what is half and all. Just for time being, you just remember it detects the hydroxide as well as the carbonate. Now, when we speak about methyl orange, it determines all the alkalinity. It ranges from 4.5, okay, till highest. So from 4.5 to all the things, maybe 10 or 12. So you will be determining all hydroxide, carbonate, as well as the bicarbonate alkalinity. We will be determining using methyl orange. It stops till 4.5 or 4.4. Beyond that, it's not going to happen. So here you should remember that the pH range from 8.3 to above, phenolphthalein alkalinity will be measuring using phenolphthalein indicator. From 4.5 to above, we will be using methyl orange indicator. Total alkalinity. Total alkalinity is total all ions ka alkalinity will be measuring. That is carbonate, bicarbonate, as well as the hydroxide alkalinity. Okay, so that is very much important. So we will be studying about neutralizing reactions and all those stuff. Okay, so first thing, whenever you will be, just imagine you have taken the water sample. Okay, now just imagine I have taken a prepared water sample by adding sodium hydroxide. Okay, so it indicates that I have added hydroxide ion, so I will find hydroxide alkalinity. So what I'll be using, okay, so what I'll be using is, so before that, I'll be just telling you in a very kind of like crisp procedure about this particular experiment. You will be taking a water sample, you will be adding phenolphthalein indicator. You will be titrating against acid solution, that is maybe zero point 0.1 normal HCl or zero point 0.1 normal sulfuric acid or whatsoever. Okay, so what I'll be doing when the acid is actually, when you are adding, when you're titrating against acid, your water sample, whatever it is there, no, it starts to neutralize. Okay, if it contains base, okay, so if it contains base, it starts to neutralize. Okay, that we'll be measuring. So neutralization reaction of this particular alkaline water will be actually, we'll be discussing right now. The first thing, I have prepared a water sample. I have added NaOH right now. So I will be having, obviously, it turns into a deep pink color when I add the phenolphthalein indicator, and it indicates that either carbonate is present or you will be having hydroxide. So just imagine I have already added NaOH. So hydroxide is present. Okay. So first thing it will be your hydroxide neutralization. I have to neutralize hydroxide. So what I'll be doing, so water sample contains NaOH. Now I have written only OH part of it. Okay. And I'm titrating it against your sulfuric acid, that is H2SO4. Okay. Or you will be having hydrochloric acid, that is HCl. So it is your proton over here. That is nothing but H plus over here. Okay. So you will be having an acidic one as well as the basic one over here. Okay, so OH minus as well as H plus. So this, okay, so when you add acidic content to the water which contains hydroxide, it will neutralize to form the water. Okay, it neutralizes to form the water. So here you have to remember that 1 mole of hydroxide ion, okay, react with 1 mole of acid, okay, to form the water or to give the water. Neutralization is done. Okay, next step after neutralizing, now from 12, 11, 10, now after reaching 10, just imagine you have added the bicarbonate. Sorry, you have added carbonate. Calcium carbonate is also there in the water. Okay, so if the carbonate is present, carbonate, when you add, the water sample contains carbonate, you are actually titrating against acid. This is a scenario. So this is the carbonate and this is the acid. So acid reacts with the carbonate to form bicarbonate. Okay. So it neutralizes to form the bicarbonate. So here you should remember that soon after it forms the bicarbonate. Okay. Soon after it forms the bicarbonate again reacts with the acid to form carbonic acid. Okay, it forms the carbonic acid, and this carbonic acid further breaks down into carbon dioxide as well as the water. This is how it happens in the normal scenario. Okay, but here you should remember that the 1 mole of your hydroxide ion reacts with the acid to form kind of like water. Okay, 1 mole of carbon dioxide, sorry, your carbonate. Okay, now it reacts with this 1 mole of acidic content. Okay, now this acid, I'm extremely sorry, acid. Okay, so it forms your bicarbonate. Again, this reacts with another 1 mole of acid to form the carbonic acid over here. Okay, further neutralization is going to happen. So here you should remember that it's only the half part of the carbonate. It's only the half part of the carbonate the answer is actually showing. That is actually this half part of the carbonate is actually getting converted into bicarbonate to 8.3 pH. Okay. Now we have this bicarbonate over here. Okay. Now this bicarbonate, okay, will be further reacting with the acid, maybe HCl or sulfuric acid, to form the carbonic acid later on. Is it clear for you? That's why if you just consider this as a pH range, okay. So here is the pH range anta ankoli. So here you will be having the pH range. Okay. So just imagine this is the 8.3 or whatever. Here is the 8.3. Till here, you will be having, this is going to measure your hydroxide as well as the carbonate, half of the carbonate. Okay, half will be neutralizing up to 8.3. Okay, you may consider it as 12 over here. Okay, that comes under phenolphthalein indicator wala concept. Remaining half of the carbonate along with the bicarbonate. Okay, along with the bicarbonate, CO3 minus. Okay, here half of the carbonate. Okay. Hmm. So remaining half of the carbonate as well as the bicarbonate, that will be neutralized, okay, by the T. Okay, or I can say in the total alkalinity we'll be measuring alba. So here by using the methyl orange, okay, indicator when we are adding it. So at that time you'll be getting the result over here. So that thing, okay, will be actually neutralized in the total alkalinity concept over here. So again, I'll repeat. So hydroxide neutralization along with half of the carbonate. Okay, along with the half of the carbonate, that answer will be given by the phenolphthalein indicator. When you add it, so neutralization is going to happen. That will be coming under phenolphthalein alkalinity. The remaining half of the carbonate, which is actually further neutralized to form the bicarbonate, and the bicarbonate further neutralizes to form carbonic acid. Again, it will be neutralizing to form the carbon dioxide and water. That will be actually measured, okay, by using the methyl orange indicator in the total alkalinity. That is nothing but T minus P. That is nothing but T minus E. Just imagine for this answer you have got, for this you have got 4, okay, 4 ml, okay. And here for total you have got 8 ml answer, okay. So here it is actually 8 minus 4. That is 4. So 4 ml to neutralize this, 4 ml to neutralize this. Okay. So, but you should remember that not all these three, that is nothing but not all bicarbonate, carbonate, and hydroxide will be actually present together in a water sample, especially your hydroxide as well as bicarbonate. Hydroxide reacts with the bicarbonate to form carbonate. Okay, that's why not all the three ions are present in the water sample at the time. Okay, that is important. So we'll go for the principle. So when we speak about this particular experiment, that is alkalinity. Okay, now alkalinity in the water is actually basically measured by titrating using two indicators, that is phenolphthalein as well as the methyl orange indicator. So first and foremost step is your phenolphthalein indicator is actually added. The water turns pink in color, it means that hydroxide or carbonate is present, or hydroxide and carbonate is present. We don't know, we will calculate and we will be telling either it is only hydroxide or only carbonate or both are present. Okay. Now, it is actually titrated against the acid, maybe sulphuric acid or hydrochloric acid is added until this particular pink color solution turns into colorless. Okay. At the pH that is 8.3. Okay. Now, this is called as phenolphthalein alkalinity. Okay. So, where all your kind of like hydroxide and half of your carbon dioxide, so not carbon dioxide, your carbonate ions are neutralized. Now, if it is phenolphthalein alkalinity, now what is the not methyl, total alkalinity? What is PA? Okay. So when we add methyl orange, okay, you can take the same sample. Okay, for that, you can add 2 or 1 drops of methyl orange indicator, or you can take another water sample, okay, same amount. And for that also, you can take the methyl orange, okay, indicator. Most of the time in the laboratory we'll be continuing with the same water sample. For that we'll be adding the methyl orange indicator 2 to 3 drops, okay, and the titration will be continuing until the solution is going to change from orange color pink color at 4.3 if you are interested. Okay. So for the usually what we will be doing in our laboratory is that so we will be taking a kind of like a water sample. For that we'll be adding methyl orange. Okay. So 8.3 is not acidic, it is basic itself, right? So when you add methyl orange, if this water sample is somewhat basic, will turn into yellow color. Okay. So our we will be usually keeping the kind of like endpoint. Okay. So when we take this yellow color ka water sample, okay, indicates that methyl orange is already added to that water sample. We'll be titrating it with an acid. Okay. Until this yellow color turns into somewhat reddish orange color. Okay, that is the end point. Some people even consider till until it reaches pink in color, but we usually stop in a reddish orange in color. Okay, so it indicates that it has been completely neutralized, and this process helps to identify the formation of kind of like identify the forms of alkalinity, and it's very important for pH control in the kind of like water treatments and other things. Okay, so that's actually the principle of this particular experiment. Okay, so what are the basic requirements needed? So we'll be requiring water sample. Okay, we'll be requiring basic or alkaline water sample. Now I've already told what's the difference between base as well as alkali. So we'll be requiring alkaline water sample and 100 ml of conical flask. Okay, we'll be requiring titration assembly, zero point 0.1 normal HCl, or we'll be requiring sulfuric acid solution. Okay, and we'll be requiring phenolphthalein indicator as well as the methyl orange indicator. So we'll start with the step one, okay, measurement of the phenolphthalein alkalinity, that is PA. Okay, so take a conical flask, add 50 ml of water sample to it, okay, and add 2 to 3 drops of phenolphthalein indicator. Okay, so if there is no color change, if water remains colorless, it doesn't turn into blue color, it indicates that the phenolphthalein alkalinity, the PA, is zero. So no need to proceed with the acid base titration. Okay. So PA is zero. It indicates that there is no hydroxide or carbonate is present. So if the water sample, okay, when you add a phenolphthalein indicator, 2 to 3 drops of phenolphthalein indicator, okay, and the pink color is going to develop, okay, if the pink color is going to develop, PA is present. It indicates that phenolphthalein alkalinity is present. Okay, so we can proceed with the acid-base titration process. Okay, so what kind of acid-base titration? We will be actually having the water sample now, which already we know that it is somewhat basic in nature. Okay, and the acid we're going to use is zero point 0.1 normal HCl or the sulfuric acid. Okay, so here the endpoint should be from the pink color to the colorless. It should turn colorless. Okay, it indicates that there is a complete neutralization of hydroxide and half of the carbonate ion. Okay, not full carbonate ion, half of the carbonate ion, and in the end you have to record the volume of the HCl used in ml. Okay, so it gives you the phenolphthalein alkalinity. The next step is measurement of the total alkalinity. Now, how we can measure total alkalinity? So you can take another 50 ml of the fresh water sample, or you can continue with the same itself, the water sample which you have used for the phenolphthalein indicator itself. Okay, so again you have to add 2 to 3 drops of methyl orange indicator. Okay, now if the thing that if the water sample is containing basic, okay, so if it is basic in nature or it contains bases or alkali, turns yellow in color. In okay, so methyl orange indicator in the basic medium, okay, it turns yellow in color. Okay, so from yellow color, you are actually titrating it against the acid. So when you add acidic solution, okay, to the basic solution, okay, now we have added the methyl orange indicator. That time, this yellow color turns into reddish orange color. So the end point is reddish orange. Now this indicates that there is a complete neutralization of your carbonate, okay, and the bicarbonate. Okay, so it will now we have to record the total volume of the acid used. Okay, please remember that if you're only using, I'll just write it here, if you're actually taking the sample separate for your phenolphthalein indicator, just imagine phenolphthalein you're using 50 ml of water sample, methyl orange you're using 50 ml of water sample separate. Okay, you have to note down the reading separately. Okay, so if you're using only 50 ml of the water sample, just imagine from 1 to 2. Okay, so 2 ml, of, sorry, 1 ml, you got the reading over here. 1 ml is required. Okay, that was a result for your PA, and you will be continuing. Okay, or I'll just consider 0 to 2 ml. 2 ml. Okay. Then from 2 to maybe 2.5. Okay. So 2 to 2.5. So overall, when I'm calculating PA, okay, so when I'm calculating PA, if you're using only 50 ml of the water sample, already PA is done. After that, you're adding 2 to 3 drops of methyl orange and you're continuing the titration. Please consider it as 2 ml plus zero point 0.5, that is 2.5 ml. Okay, 2.5 ml for PA. If you are using 50-50 separately, here it will be 2 ml. Okay, that is 0 to 2, what you're getting the readings. Okay, here it will be from 2 to 2 to 3, 3 to 4, 4.5. So when you're calculating how much volume is actually required, you will be getting it as 2.5 ml. I hope the concept is clear for you. So if you're taking two separate samples, sorry, so if you're taking two separate water sample is same, but once for PA you will be taking 50, once for PA you're taking 50, you will be getting the result like this. If you're using the same 50 ml water sample, after finishing PA, you will be continuing with the TA. Please consider 2 ml what is there in that TA. This 0.5 ml whatever is there. Okay, 2 to 2.5 over here. That is 0.5 ml. So 2 ml plus 0.5 is 2.5 ml for your 2. So there are two options. Okay, that will tell you the total volume of the acid used. Okay, so that is total alkalinity tells about hydroxide as well as carbonate and bicarbonate ions content present in the water sample. Okay, but please remember that not all the three water samples, sorry, not all the three ions can be present together in the water sample at the same time, especially not hydroxide and bicarbonate. Okay. Fine. So, water analysis, I've already told you there are two stages of acid titration. Okay, phenolphthalein alkalinity and total alkalinity. Okay, so phenolphthalein alkalinity. Okay, so titration from the sample's initial pH will be usually 8.3. Down the 8.3, you're actually measuring the pA, that is total alkalinity, will be continuing from 8.3 to 4.5. You will be getting the TA ka answer. 8.3 to above that TA answer you will be getting.
Hello, my dear little bugs. Welcome back to my channel yet again. Ever wondered how much alkaline your water really is? Alkalinity is the water's ability to neutralize acids, mainly due to bicarbonates, carbonates, and hydroxide. To check the phenolphthalein alkalinity, take 50 ml of water sample, add 2 to 3 drops of phenolphthalein indicator, and titrate it against acid like 0.1 normal HCl or sulphuric acid until the pink color turns colorless. Phenolphthalein indicator turns pink in color only if the water contains base or alkali in a higher pH more than 8.3. To check total alkalinity, take 50 ml of water sample, add 2 to 3 drops of methyl orange indicator. In a basic condition, it turns yellow in color, and titrate it against 0.1 normal HCl or sulfuric acid until it turns into somewhat reddish orange in color. That is the end point. So it tells it all the like carbonates, bicarbonates or hydroxide has been completely neutralized in the water sample. Remember that all the three, that is carbonate, bicarbonate as well as your hydroxide ions, cannot be present together at a time in the water sample. So I've just shown you, this is the yellow color, the initial stage. As we added, titrated against sulfuric acid, it turned into reddish orange color. Here are the observation and calculation part. And here is a result section. I have already uploaded the video, entire detailed description regarding how to calculate it. So please watch the video, like and subscribe. Thank you.
I hope that the protocol is somewhat clear for you. Now, to calculate the phenolphthalein alkalinity as well as total alkalinity, that is PA and TA, we can use this particular formula. Okay, so you can pause the video and you can take it down. Okay, or you can take a screenshot. Okay, how to calculate the phenolphthalein alkalinity. Just imagine, okay, for PA, okay, volume of 0.1 normal HCl used. We'll take the previous example itself. It was 2 ml. So 2 divided by 50 into 1000. Okay. For your TA, it was 2.5 ml. 2.5 divided by 50 into 1000. You will be getting the results. Okay. Now, this is the observation table, observation and calculation table, initial, final, as well as the volume of 0.1 normal HCl needed for PA as well as PA. Now, we'll be focusing how to interpret the result after calculating the answers. Okay. So you can just pause the video and take a screenshot, or you can write down this particular table. We'll be discussing each one of the case in detail, how to interpret the result and what does each scenario mean. Okay, fine. So this is a particular table, okay, we'll be discussing. So in this, there are different conditions or different cases. Okay, so before that, I'll just tell you, like low or kind of like low to neutral pH, that is somewhat like 6 to 8.3 or 4 to kind of like 8.3. Many bicarbonates are actually mainly in this particular water sample, you will be having bicarbonate. Okay, hydroxide as well as carbonates are usually low or absent if it is less than 8.3. That we have already discussed. If it is 8.3 to 10, if the pH range is 8.3 to 10, okay, so it is somewhat moderately alkaline water sample you will be having, and mainly it contains carbonate. We have already discussed. Okay, half carbonate. Okay, so carbonate and the bicarbonate may be present. Coexisting is happening because carbonate, when it reacts with the acid, you will be getting the bicarbonate. So that is present. You have the higher pH, above 10, like 11, 12. Okay, you will be mainly having hydroxide with some amount of carbonate. Dominantly, you will be having hydroxide ions. Okay, bicarbonates are absent. Sorry, the bicarbonates, okay, ions are mostly converted into carbonates and bicarbonates are absent. Okay, if the water sample contains it, because bicarbonates react with the carbonate. Okay, sorry, bicarbonates react with the hydroxides to form the carbonate. That's why bicarbonates cannot be seen. Here, you should remember that all the three ions cannot be coexisting together in the water sample, right? So I have written the formula over here. So if the water sample contains hydroxide, if the water sample contains bicarbonate, they react with each other to form carbonate and water. Okay, so that's why all the three, especially hydroxide as well as bicarbonate, cannot be present or cannot be coexisting together. Okay, so we'll be discussing each case one by. So let us understand how to interpret the result. Okay. So I have titled the water sample and I got PA, that is phenolphthalein, and alkalinity, okay, is 30, and PA, total alkalinity, as 100. Okay. So we'll understand, okay, by interpreting this particular result by using the table. Okay. So now my here P is equal to 0. That is phenolphthalein alkalinity is 0. Now, can we use this? We cannot use this because I got the result as 30. It indicates that where I have taken the water sample, I have added the indicator, that is phenolphthalein indicator, and it turned into pink in color. So I did acid base titration over there and I got the result 30. So this is ruled out. That is P is equal to 0 is not possible. We cannot use this condition or the case. The next, T is less than half of T. Now P is 30, half of T is 100 divided by 2, that is 50. Okay, so 30 is obviously less than 50, so I can use this condition. It indicates that these 1, 2, 3, 4 condition is not possible. Only this condition is possible, or only this case is possible. So I'll be taking, okay, we'll be using this particular condition or the case. So this row indicates P is less than half of 2, 30 is less than 50. Okay, it indicates that hydroxide, okay, hydroxide ion is not there. It is 0 mg per liter. Okay, carbon, a carbonate ion is present. It is 2P. It is nothing but P is 30. 30 into 2 is 60, 60 mg per liter. And you will be having bicarbonate in this particular water sample. T minus 2P, T is 100. Okay, 2P is 60, that is 40. Okay, that's why 40 plus 60 is 100. Total alkalinity is 100. So 40 plus 60, total alkalinity is 100. In this total alkalinity, 60 mg per liter is carbonate, 40 mg per liter is bicarbonate. No hydroxide is present. I have already told you hydroxide and bicarbonate cannot be present. How this table is actually formed, how it is actually interpreted. Calculation, I hope it's clear for you. So what is 2p? What is p minus 2p? That we will be studying one by one. We'll start with the case 1. Okay. So condition is p is equal to 0. So in this particular case, hydroxide alkalinity cannot be seen. Carbonate alkalinity cannot be seen. Only bicarbonate alkalinity is seen. Okay. So in this particular one, I'll explain you. I have taken the water sample. When I add phenolphthalein indicator, it doesn't turn into pink in color. It remains colorless. Okay. It remains colorless. It doesn't turn into pink in color. Okay. So at that time, it indicates that it doesn't have hydroxide. It doesn't have it doesn't have carbonate. It only contains bicarbonate. Okay, so we have already discussed phenolphthalein, hydroxide, and half of carbonate, methyl orange, all the three. So T minus P is half of carbonate as well as the bicarbonate. Okay, this we have already discussed, right? So T minus P is nothing but methyl orange minus phenolphthalein. That is nothing but we had got the result 100 as well as we have got the result 30 alva. So in this 100 minus 30 is 60. That we will be measuring over here. Okay. So that is the answer for this. Okay. So in that 60 you can just tell T minus P. Okay. That result you will be getting over here. But we'll be studying that later. So in case 1, if P is equal to 0, it indicates that when we add phenolphthalein indicator to our water sample, it doesn't turn into pink in color. It remains colorless, indicating there is no hydroxide, there is no carbonate, there is only bicarbonate. the volume or the amount of 0.1 normal HCl or sulfuric acid added to neutralize only bicarbonate will be your TML. That is nothing but your total maybe that time we had taken 2.5 L. So 2.5 ml. You can just write over here. If you get the result 2.5, that's it. Okay. So bicarbonate will be ml. Solely total alkalinity volume we will write it. Okay. The next case 2. Okay. P is equal to half of T. Okay. So P is equal to half of T. So it indicates that there is no hydroxide, there is only carbonate and there is only bicarbonate. Okay. So, sorry, there is no bicarbonate, meaning it says that there is only carbonate is present. So, how we can say 2P over here? Okay. So, what is this 2P? Okay. So, here if you remember that, we'll just take a basic example. T is 20 and T is 40. Okay, just a rough example. Just imagine T is 20 and T is 40. Okay, T is 40 ml. Okay, so according to this particular statement over here, okay, so P is equal to half of T. Half of 40 is 20. So 20 is equal to 20. It indicates that we know that only carbonate is present. Why? Because I'll tell you, half of the carbonate. Now, just imagine 20 ml of the carbonate is required to neutralize that half carbonate present in this particular section. Okay, and remaining half of the carbonate will be used by the methyl orange indicator wala section. That when you treat it with the acid one. Okay, 20 ml to neutralize carbonate, 20 ml to neutralize the remaining half of the carbonate. That's why you will be getting only carbonate answer. Again, I'll repeat. Okay. So, why in this condition carbonate you will be having? Just imagine T is 20, T is 40. So, 40 divided by 2 is 20. 20 equals 20. 20 ml is required. Okay. As it suggests now, total alkalinity anta bandaga, you will be having P is equal to half of T. In this total alkalinity, if you are telling 40 ml, and in this P, it indicates that it is 20 ml. Okay, 20 ml is required only to neutralize this half of the carbonate. What about remaining half of the carbonate? That is done by this methyl orange wala indicator. When you add methyl orange indicator, when you titrate it against acid, okay, that answer what you get is 20. So if you're doing it in the same 50 ml ka water sample, just imagine you have taken the conical flask over here, you're titrating it against it. So just imagine for TA you got 20 ml. Okay, for again TA, okay, when you added it, so just imagine you got it 0 to 20 is 0 to 20, that is equal to 20 ml. Okay, then 20 to 40, that is also indicating that it is 20 ml. But for TA we will be considering this will become your TA. Okay, sorry, and this will become your TA. That is from 0 to 40, from 0 to 40. From 0 to 40, that is 40 ml, what we have written over here. Okay, so 20 ml to neutralize this half of the carbonate, remaining half of the carbonate to neutralize for the remaining section, that is T minus P, that is remaining 20, the half of the carbonate. That is T is nothing but this result what we have got. We'll consider this as T. I'm extremely sorry if I'm making confusions for you. We'll consider it as T. We'll consider this as P. Okay. So when you add phenolphthalein indicator, half of the carbonate got neutralized, 20 ml. Okay. Then again you added methyl orange indicator. Okay. Again 20 ml was required to neutralize half of the carbonate. But we will be considering it from 0 to 40. That's why it is 40 ml over here for total alkalinity. Okay, so this concept I have already explained in the previous slides. Okay, you can go back again if you didn't understand here. Okay, so here it indicates that only carbonate is present, nowhere hydroxide as well as bicarbonate. If hydroxide would have been present, you won't be getting 40 here, you would have got 45 or 50 or something like that. That we'll be studying in the next cases. The next case is case 3, P is equal to so when we say P is equal to 3, okay, only hydroxide ion is present in the water sample. Okay. Now, as we all know, phenolphthalein indicator, it is going to measure phenolphthalein alkalinity, hydroxide and half of the carbonate, methyl orange, okay, total alkalinity, all. hydroxide, carbonate as well as bicarbonate. But please remember, all the three will not be present together in a water sample. Okay, T minus P is half carbonate as well as the bicarbonate. Okay, now here you should remember that. Okay, here you should remember that is equal to T. T is equal to T. It indicates that you have done the titration and you have taken 50 ml of water sample. You have added phenolphthalein indicator. After adding phenolphthalein indicator, you have titrated against acid, okay, that is HCl, okay. After that, you got the result as 20 ml over here. Just imagine you got the colorless endpoint. Oh, so endpoint is colorless, 20 ml, 0 to 20, so 20 ml you have got. Then you have added methyl orange. You have added methyl orange, you have continued with the titration, no need to continue. Okay. So you have added methyl orange. Here, suddenly it turned into orange color. There is no yellow color. Directly endpoint has come. Okay. So at that time, okay, so beyond the phenolphthalein endpoint, if it actually consumes HCl, that is P minus P beyond phenolphthalein endpoint. Just imagine I have taken consumed 20 ml for phenolphthalein indicator and I got extra 1 ml, that is 21 ml. I will just add it for TA. So extra 1 ml I have consumed to neutralize the remaining carbonate. At that time, okay, at that time it indicates it is T minus P. Okay. So this indicates it's a T minus P. Okay. So now here we are not considering T minus P in this particular section because we have not utilized an extra acid to neutralize the what you can say base present in our water sample, because all the bases present in the water sample has been completely neutralized by this particular phenolphthalein indicator when we have added. So it's completely neutralized in this 20 ml of acid. Okay, so that's why we got indicator from pink color to the colorless. So when you add methyl orange to that, no need to further neutralize it because you directly got the orange color when you added the methyl orange to that particular water sample. So at that time, volume of 0.1 HCl added to neutralize only hydroxide is actually P ml or T ml. So you can just imagine you have taken 50 ml of water sample, phenolphthalein indicator, added you're titrating it against acid. Okay, you got 20 ml. P is equal to 20 ml. No need to add methyl. So you have added methyl, you got the result there only. Okay, it indicates that it is only 20 ml. Or you have taken extra 50 ml of water sample, you have added methyl orange to it again from the beginning. Now you have not taken the PA wala, phenolphthalein indicator wala water sample, separate water sample. For that you are adding the what you can say methyl orange indicator. Sharp to the point 20 ml, you will be yellow color will turn into orange color. So TML or PML. So either it is PML or TML. If you're using the same water sample, continuation to your phenolphthalein one, then you cannot write TML. If you're using only when if you're using different water sample, then you can take TML over here. So it indicates that either P or TML. Okay. So 20 ml will be your answer for this. So let us go to the last case. P is less than half of P. So just imagine your phenolphthalein alkalinity answer you got as 20. Total alkalinity answer you have got as 50. So 50 and the halite, 50 divided by 2, that is 25. So 25 is actually greater than 20. At that time, you'll be using this particular condition. Okay. So at this particular state, what will be your answer? So you should remember that 20 ml of this particular this one what you can say whatever you have added the acid 20 ml was required, acid content was required to neutralize the half of the carbonate. Okay, half of the carbonate, and you have 50 over here, alva. So here you should remember that total alkalinity contains 20 plus 30. 30 for your methyl one. So I have already told you T minus P. T minus P is nothing but 50 minus 20. 50 minus 20, that is 30. So remaining 30, whatever you have it, that is going to neutralize bicarbonate as well as the half of the carbonate. That's why the volume for your zero point 0.1 normal HCl added, that is neutralized carbonate, will be here 20 ml, and here what is that particular ml? That is nothing but 20 plus 20. Okay, 2 times the P, 20 into 2, that is 40. Okay, so answer will be 40. Okay, the remaining one, the volume of 0.1 normal HCl added to neutralize the bicarbonate minus 2p. Now P is actually 50 minus 40, that is 10 ml. So 10 ml to neutralize bicarbonate, 20 plus 20, half was neutralized in PA, half of neutralized in TA. Okay, so 20 plus 20, 40 will become your carbonate का answer. Okay, and this is your result. You have to write what sample it is, how much is your PA result, how much is your TA result, and looking into the PA as well as TA ka result, looking into the condition, is it case 1, case 2, case 3, you will be solving and you will be writing the answers over here. Is it 0, 0 and T? If it is T is equal to 0, okay, so those things you will be calculating and you will be concluding the experiment. Thank you.